Hello everyone, I'm Engineer Jomar A.C. Lau.
And I am Engineer Robert B. Miranda, and we will be reporting today on
Sensitivity
sensitivity
and
and
robustness
robustness analysis
analysis
in
in
feedback
feedback
systems.
Feedback systems play a crucial role in engineering and control applications, ensuring stability and optimal performance in dynamic environments. However, these systems often encounter uncertainties, variations in parameters, and external disturbances that can affect their behavior. To address these challenges, sensitivity and robustness analysis are employed. Sensitivity analysis examines how small changes in systems parameters and impact performance, while robustness analysis assesses a system's ability to maintain stability under uncertain conditions. These analyses are essential for designing reliable and efficient feedback systems in various real-world applications. Sensitivity analysis examines how changes in system parameters affect the system's output. It helps identify critical parameters that influence performance and ensures that the controllers minimize sensitivity to variations. For example, in medical devices, in devices such as pacemakers and insulin pumps, sensitivity analysis is conducted to study how small variations in voltage, signal parameters, or medication dosage affect functionality. Another example is in robotics. In robotic arms used for precision manufacturing, sensitivity analysis is performed to evaluate the impact of small variations in motor torque, sensor readings, and environmental factors. Testing is conducted in control lab environments and simulated real-world conditions to fine-tune control algorithms for optimal performance. Robustness analysis evaluates a system's ability to maintain stability and performance despite uncertainties and disturbances. A robust system remains stable even when conditions change. For example, in automotive cruise control, robustness analysis is applied to assess how a vehicle maintains a steady speed despite road inclines, wind resistance, and varying load conditions. This testing occurs in real-world driving scenarios, wind tunnels, and simulation environments to ensure reliability across diverse conditions. Another example is an airplane autopilot. Engineers perform robustness analysis on autopilot systems to evaluate their ability to maintain stable flight despite turbulence, varying weight distributions, and sensor inaccuracies. This involves simulations, wind tunnel tests, and real flight testing to validate system performance under different weather and operational scenarios.
Now, let us discuss the mathematical description or the math behind these concepts. So first, we have here our basic control system or our basic loop diagram for a closed loop system. So we have here our RS or our reference signal input, and then it will go to our system, okay, to our control system. And we have our CS and GS representing our compensator and our plant gain. And then finally, we have our output YS. Okay, so I think we're very much familiar in this basic diagram, in this loop diagram. And also, this is the equation that can explain or represent the output YS. So YS is given as GSCS over 1 plus GSCS multiplied by our reference signal input. Okay, so this is already a very familiar equation for us because it was already discussed by previous reporters. So now let's proceed to the next slide where we actually define what is sensitivity and robustness. How do we define it mathematically or numerically? So first, again, we have here our simple loop diagram, and we can see here the sensitivity function. So how do we define sensitivity? So sensitivity or sensitivity function is actually defined as SS equals 1 over G plus G S CS. Okay, so if we take a look at this equation, we can see that the higher the GS or higher the CS, our SS will actually go down. Actually, if we plug in higher and higher value of GS and CS, our SS will approach 0. So that's the most important thing to remember about sensitivity function. The ideal value of sensitivity function is actually 0, because if we have a sensitivity function value of 0, our system will not be able to sense, will not be able to detect, therefore will not be affected by any external or environmental disturbances or noise coming outside our system. And then, how do we define robustness? So actually, we define it using the complementary sensitivity function given by this equation. So why do we call it complementary sensitivity function? Because actually, if we add the sensitivity function and the complementary sensitivity function, we will get a value of 1. Okay, so complementary sensitivity function gives us a numerical representation of the robustness of the system. And if we take a look at this equation, the ideal value for complementary sensitivity function, or the ideal value for the robustness of the system, is actually 1. Why? Because again, we said earlier, if we add these two functions, this sensitivity function and this complementary sensitivity function that is representing our robustness, if we get a value of 0 for sensitivity function, which is what we want to have a sensitivity of 0 rather, our robustness will be 1. Okay, so now let's proceed to the next slide. Okay, so I have shown you a sample of a basic equation representing our system, an ideal system. That means no disturbance, no noise coming from environment. And this is actually this term, the ys is equals to GSCS all over 1 plus GSCS multiplied by some reference signal input. However, in reality, we are actually dealing with different controllers that has different sensitivities and robustness, and also the fact that all systems experience some sort of disturbances or some sort of noise. Okay, so that's why we have this term, 1 over GSCS, rather 1 over 1 plus GSCS multiplied by our NS. So NS here is the noise function, so or disturbance. So we can see this as some sort of signal, unwanted signal, going into our system and being multiplied or being amplified by this term. So what is this term? Actually, if we go back a slide before, this term is actually our sensitivity function. So that means if you want to take a system, or if you want to make a system that is not sensitive to any sort of disturbances or noise, there's two ways that we can achieve that. First is actually by creating a control system that has a sensitivity function of 0, okay, therefore a robustness of 1, or we eliminate all the sources of noise or disturbances, which is very hard to do. So I think that's why we need to really understand how sensitivity and robustness works in our control system, because there's no way to fully isolate our system from different noises and from different disturbances coming from our environment. So to better understand or visualize these concepts and this mathematics, I will show you some simulation. So we will simulate some hydraulic system in phase fluid sim to see how different type of control system. We will compare a proportional control system, which is a very basic control system, and a PID control system, which is much more robust. So later on we will see why PID is more robust than a basic proportional control system. So let's go. Let's proceed to our simulator. Okay, so we have here our fluid sim. Okay, and then right now this is set as a proportional control system. So that means we only have a value for Kp, and then Ki and Kd is set to 0. Okay, so that means Kp here is actually the gain of our system. So proportional gain of our system. And then we have here our cylinder. So this system is actually a hydraulic system wherein we want to control the displacement of our piston. Okay, so this specific circuit here simply wants to maintain our piston at the center of our cylinder, which is around 5 cm for this simulator or for this simulation. So that's the main objective of this circuit or this control system. We want to make sure that our piston is at the center position. So let's try running this one, but I think we are going to have a problem simulating this while being recorded. So I will take some screenshot of this simulator, and then I will show you here. I will show you the simulator here. Okay, so right now if we set this value to 2, and then let's set the internal leakage. So we have here our internal leakage of 0. So again, it's like a very ideal cylinder, no? Because there's no internal leakage, but in reality there's always some sort of leakage. So if you're familiar with pneumatic or hydraulic systems. And then we also add some external loads and some other parameters like the maximum stroke, the material. So we have here friction for steel on steel. Okay, so this is the parameters for our simulation. Then if we simulate this one, we will actually see that the basic proportional control system was able to maintain the set distance or the set position of our piston. It was able to achieve around 5 cm. Okay, so there's some sort of very small oscillation, but it's very negligible. It's oscillating between 5 to 5.01 cm. Okay, and right now let's try adding some disturbances to our system. Okay, so just what my groupmate presented before, these disturbances can come from different parameters, from different aspect of our mechanism. So for example, our hydraulic cylinder here is old. Okay, so we are introducing leakage to our cylinder gaskets. So it's a common error or common problem when you're dealing with hydraulic system and pneumatic systems, that you get lots of leak as the system gets old. Okay, so let's try doing that. And then let's try adding 1 liter per minute here. So that's a huge leak. Okay, so represented by a huge leak. Okay, so now let's try running that one. Okay, so as we can see, what happened here. So initially our system, our basic proportional control system, was able to maintain or achieve the middle position or the 5 centimeter displacement of our piston. However, by introducing disturbance to our system, our control system is not able to maintain our target position, our target signal essentially, okay, or our reference signal rather. Okay, so right now we are reading at around 5.25 or rather, yeah, 5.25 centimeter. Okay, so that is a huge error for our control system. We want to maintain a 5 cm displacement and we are getting 5.25 centimeters. This is a big error for a control system. So what can we do? So what can we do is actually use a more robust control system, such as a PID controller. So PID controller is known in different industry to be a robust and what do you call this? Tunable. Yeah, it is a very tunable. If there's a word such as tunable, that I just want to say that you can tune it. If you want to make it very robust, yeah, you can do that. If you want to make it less sensitive, yes, you can do that. So let's try doing that. I have here a table for Peasant integral rule, which is the value that we got from the Ziegler-Nichols method. Okay, so let's try plugging that in our simulator. So let's try plugging that in, that values. Okay. Okay. And then let's try to simulate that now. Okay, so again, we are still dealing with the same disturbances of internal leakage of 1 liter per minute. So let's try that. So as we can see here, our system was able to achieve around 5 cm. Okay, it's oscillating between 4.99 to 5.01, which is very good. Okay, it's very good comparing to the 5.25 error or 0.25 error of our crude proportional control system. So this is a very big increase in the robustness and reliability of our system. So I think that's the reason why PID controller is very popular and commonly used in different types of industries. Okay, so we can also simulate this. Let's try again. Let's try to simulate this using zero leakage. Okay, let's run that. And as we can see, our PID is still able to maintain the 5 centimeter target or the middle position target for our system. Okay, so to summarize everything that we have discussed so far. So first, sensitivity SS measures disturbance rejection and process variation effect. Okay, so as we have seen in our calculation and in our simulation, when we use a system or a control system that has low sensitivity and a good robustness, we can reject the variation in our process, or we can reject the disturbance from our environment. And then that's why we are able to maintain stability. Okay, so we are still stable under uncertainties, or actually because we don't know if our system will have 1 liter per minute leak or 0.5 meter leak. So we have less of uncertainty. But as long as your design is robust, you consider the robustness of your system, so we will have a reliable system. Okay, and then again, the fundamental relationship of SS and TS, the sensitivity function and the complementary sensitivity function, they are equal to 1. Okay, so SS plus DS is equals to 1. And then we have here some practical considerations also. So design trade-offs between performance and sensitivity. Okay, so one way to increase, or rather to decrease, the sensitivity of the system for a proportional control system is actually increase our KP value, our proportional gain, or our system gain. However, it will result to a much robust system. However, the performance might suffer. Okay, so if you apply bigger proportional gain to a proportional control, I think we know what will happen. It will oscillate. Okay, so it will oscillate. So depending on the application, if you really want a very low sensitivity system and you don't worry about the oscillation of your system, then it's okay. And then we also have gain and phase margin indicate systems, and the Nyquist plots provide visual stability. So these are the other techniques that we can visualize our sensitivities. Okay, so I think these two topics will be discussed, or this was discussed by previous and future presenter in our class. And then also, here's some basic rule. Okay, so for a well-tuned system, the sensitivity function must be around 1.2 to 2.0. So anything greater than that, we will have a very sensitive control system. Okay, and then for the complementary sensitivity function, we can have from 1 to 1.5. So yes, our sensitivity function and complementary sensitivity function can have a negative value depending on the gain of our system or the feedback of our system. And then second, feedback reduces system sensitivity to variation. Okay, so that's why we can see in our simulation earlier that when we utilize a more robust feedback control system such as a PID control system, we achieve a much more reliable or much more robust output. And then robustness analysis is essential for real-world implementation. Okay, and last, balance needed between fast response and, of course, stability of our system. So I hope that's everything that we have discussed, or I hope that we have learned what is sensitivity and robustness in control systems. And if you have any questions, you can reach us in this email address. So we will be putting our email address at the bottom. Again, I am Engineer Robert D. Miranda, together with my co-presenter, with my co-reporter, Engineer Jomar Silao. Thank you very much and hope to see you in the future. Thank you very much.